Hi everyone, welcome to 106A. Today we'll be giving an introduction to ROS. So first we'll do an overview of ROS. We'll dive into communication, build systems in ROS, CMake, and packages. What is ROS? Well, ROS stands for Robot Operating System. It's a set of open source software that includes some libraries and tools that will be really helpful for working with robots. Some of the benefits of using ROS is that it handles some of the low-level device control and hardware. We work a lot with hardware in this class, and you don't want to have to worry about every single little detail of how the hardware works. Someone else has written that code, and we want to just be able to plug it into our code. That's where ROS comes in. It will let you use other people's code. It will handle the communication between your code and their code. It supports multiple languages. In our class, we'll primarily be using Python, but it also can work. ROS works with C++ and Lisp. It's also used in research and industry, and handles builds and packages for you. So first, communication. Some of the key terms that are important in ROS communication are nodes. Nodes are processes that perform computation. If you have a motor on a robot, that motor will run some lines of code to turn a command like turn left 90 degrees into a precise motion in terms of a rotation, perhaps. But that command that motor receives needs some way to reach that motor, right? So that's where the topic comes in. A topic is a queue over which nodes exchange messages. A topic is used by two different types of nodes, a publisher node and a subscriber node. The publisher node is a node that sends messages to topics, and subscriber nodes receive messages from those topics. So here's an example. We have Pacman here that is a subscriber node, and Pacman, every time it reads a message, will increase its score. And here's a publisher node, this assembly line, that's going to create pellets. So right now, Pacman is set to reading this topic. And so if it reads a message, it's going to increment its score. So right now, it saw a message and it incremented its score. But we also just stopped reading the topic. So you can see, despite the publisher continuing to publish messages, Pacman's not reading it. Now Pacman is now reading the messages again, and we can see that it read the message and the score incremented again. So you can see that the publisher, subscriber, and the topic are all decoupled. You can have all of them reading and writing at once. You could have nobody reading or writing. You can have any combination of this. In our class, this is an example that maybe we were more related to our class. In mobile robotics, maybe you have a mobile robot and you want to operate it with your keyboard and a joystick. So you have two publishers, and your mobile robot has two motors on it. So topics work in this case as well. You can have your two publisher nodes, the keyboard and the joystick, published to this command velocity topic, and have two motor nodes, their subscriber nodes, read from that command velocity topic. And this works. Another key term that you'll need to know is ROS master. ROS master is a registration list for ROS nodes. It's how ROS nodes know who it can communicate with. So here are some benefits for using ROS communication. Multiple, single, or no publishers and subscribers can exist for a single topic, and this can change in real time without any issues. There's standardized and abstracted communication, and this communication model enables microservices architecture instead of a monolithic program. All these nodes exist separately as a small different service, instead of having all this code live in one place so it can all work together. Here are some additional resources on ROS communication. CMake. CMake is our build system that we'll be using in ROS. Why use a build system though? If you write an application, some source code, maybe some Python code, and you want to automate the compiling the source, you don't want to have to run gcc myapp.cpp for every single file of source code. And there's different configurations for different platforms. You don't want to have to worry about that. You want to worry about writing the high-level code that will do what you want, not every single small build system thing. So you use this. It helps you link to other libraries. You can distribute your application so other people can use it, and you can run some tests. So CMake will control the software compilation process, and it'll be described in a cmakelist.txt file that is partially generated but partially written by you. You'll write out some of the things, like some of the libraries that you'll depend on. And CMake will generate some native make files and workspaces that you can use. So this is what the build flow looks like. Here's your CMake list file, and that will get converted to a make file, a .obj file, and then a .exe file that you can actually run. Finally, packages. So before we get to packages, we need to look at the workspace where our packages will live. So first, we have our build file. So CMake, list, and catkin will keep some cache information and intermediate files in this space. You won't have to worry too much about build in this class. You have devel. This is a subdirectory containing the final build products, which can be used to run code. We'll also have setup.bash, which you'll need to use to get some environment variables for your work. And finally, the source. This is where your code will live, and the cmakelist.txt. It also contains all the packages. So in each package is going to exist in each package will exist these different files. It includes another CMake list, a package.xml, which includes package information and dependencies, some source files, and these are your .py files. This is like scripts, right? So you can do linear algebra in this, you can send commands to your motors, and then you will finally have your launch files. And your launch files are meant to run your .py nodes. It will start up a node, and you can run this via SSH. So here are some instructions for how to properly set up your ROS workspace. You'll be going through this in Lab 1. So if you're ever confused, go back to this. You'll need to use this constantly throughout all the labs you'll have in this class. Here are some additional commands that will be useful. First is ROS core. ROS core must be running for ROS nodes to communicate. So just type in ROS core on a terminal and you'll be good to go. You have ROS run, and ROS run runs a ROS package executable. So your Python file, you'll use ROS run to run that Python file for ROS. You have ROS launch, which starts ROS core and any local nodes or remote nodes that you need. So if you have a launch file, that launch file will specify this Python node that you create and will run it, and you can run this remotely. And finally, ROS bag. So maybe you want to record a topic. ROS bag will help you do that, and it'll actually let you play back that topic as well. So if you're doing some debugging, this could be a really helpful resource. Here's some additional links that will be helpful for you if you're ever confused about ROS. Good luck this semester, everyone. Thank you.